Good afternoon. As you know, Dr. Haftka is out of town, so I'll be taking over the Wednesday and the Friday lecture. I just want to start by clarifying some of the problems people had with bonus assignments. So one of the questions was, when is the last week's bonus assignment due? And Dr. Haftka said that you'll have chance until this Friday for last week's, and Mondays of this week will be due on Friday, and it'll progress normally from this Monday. So, and the other thing is, some people ask me if they can post all their answers in one discussion, and just to make it easy for me and for the people that are voting, just each answer that you give it in a separate discussion thread, so that we can just tally up the replies to that thread for the votes. And is there any questions on this bonus assignments that people are still confused about?
The one that was given was due today?
No. Last week's, which is Fridays, is due on this Friday. So you'll have a full week for it, not just 2 lectures.
Okay. The 2 lectures thing will start
from this Mondays, yeah. So this Mondays is due on Friday. Okay. And you can vote for 1 week after the due date. So after the due date on Monday, you can vote until the next week on Friday. Sorry. So after the bonus assignments are due this Friday, you can vote until next Friday. That's.
And by voting, we add a reply to the one we think is the best.
Yeah, just reply with your name, and you say you vote for this result, and then also on all of the assignments and the votes, just send me an email too. And please don't send all your votes in one email. Just send them like you would the replies. Send them separately, so it's easy to tally up. Because I'm just going to go in my inbox. I'm going to create a folder and dump all the votes in one particular folder for one bonus problem and add them up. So I don't want to go read through every email just to see which one you voted for. It'll take me a long time. Okay.
So you want an email for the answer and an email for
The vote.
2 separate emails?
Yes. And for the what was I going to say? For the answer, for the vote, you can also just send me an email. You don't need to, if you wish to stay anonymous, you can just send an email. You don't need to post it on the discussion thread itself. So if you're worried about offending somebody, just do it through email. Okay. Mm-hmm. No, the answer is the answer to the problem. You have to post that on the website. But if you wish to vote for your friend or for somebody else, and you don't want him to know that you didn't vote for him, you can vote anonymously. So that's it.
I'm trying to find out how is the grading different for actually posting an answer and just voting.
The answer will get you about 1% total, and the vote will get you 0.05%, I believe. I'm not sure. Dr. Haftka is still going to decide about that. Yeah. It also depends on, he's gonna scale it at the end of a semester so that the maximum anybody can get is 10%, and the rest of the class will be scaled by that, just to be fair. Okay. So if you have a perfect score, you can only get 10%, and your perfect score will be used to set the scale for the rest of the class.
So only one person can get the answer, right?
No.
Yeah, if you submit an answer, only one person gets
Oh, per bonus problem? Yeah. But you can get the full 10%. Multiple people can get the full 10%. So the full bonus percentage, you can still get it, even though you don't have all the answers right.
Oh,
Okay. Are there any other questions on the bonus methods? Okay, some people came to me about the topology optimization too. I didn't have the answers they asked me of, but if if you should send me the questions you have, any questions you have on the topology optimization lecture, I'll collect it all. I'll try to figure out what I can, and the rest of it I'll ask for Dr. Haftka when he gets back on Friday, and I'll just make sure that he addresses those issues in a lecture in the future. So if there are still questions on the topology, just send me an email, please. Okay. So getting on to lecture. Okay, I'll be talking about sequential linear approximation. This is basically just an extension of the local approximations that Dr. Haftka did in previous lectures. So the reason for using this is if you have a problem where one of the functions that you're evaluating is very expensive computationally. It's like for example, the homework problem we did. If you were trying to minimize the beam weight while still satisfying constraints, the objective function was relatively cheap to go evaluate. It's just the volume times the density. So that's not a big deal for a computer to do. But on the other hand, the stress calculation required a finite element calculation. So that was fairly expensive. So this method gives you a way to just approximate expensive functions like the stress calculation and use the approximation to optimize.
So because it's such high computational cost, it's never going to be an analytical function?
No. Usually it's something like a FEM or a CFD calculation.
Okay. And obviously you have to have the constraint function, discrete values of it throughout your entire space?
No, you'll see that you start with an initial point and then you construct your approximation at that initial point and then use the approximation to calculate your search direction. And then you take a step and from that step you construct a new approximation and you iterate through that until you find the optimum.
Okay, but you have to have then at least the point, and you have to be able to, how do you calculate the derivative to get to that? Because you have to have 2 points to calculate the derivative.
Yes.
So what I'm saying is if you start at one function evaluation, then
Yeah.
you then have to have another function evaluation at a discrete point away from that.
Well, I didn't include the functions that you consider expensive are f, your objective, your constraints, and the derivatives.
Right.
So obviously if you have a very high dimensional function and you need to calculate the derivatives, that's also going to be part of your one of the expensive calculations, so you can approximate that too.
Right.
So
But to approximate it,
you need a finite differencing scheme, yeah.
right.
Yeah.
So you're going to have to evaluate it at a couple of points,
Yes.
and then you extrapolate out from those.
Yes,
to
that's
other ones.
yeah. Okay, so for this algorithm, usually the cost of optimization is less than the cost of evaluating these three functions. So just to explain the method itself, if you have the standard optimization problem formulated like this top 2 lines, you'll start with an initial design point x0, and you'll obtain a linear approximation around this point of the objective function and the constraints, and this is done by first order Taylor expansion. So you can reformulate the optimization problem as done here on the lower half of the slide, and also you constrain the step size. So when you start off with your initial design, you create the approximations, and then you optimize using those approximations. But your optimization, the maximum step size you can take for the next point that you're going to construct the local approximations at is limited by move constraints. And these move constraints is just a lower bound and upper bound for each dimension. So if we illustrate this graphically, for one-dimensional case, you start off at x0. you'll have the objective function, and you construct your local approximation at x0. You calculate the gradient, and then you obviously want to improve your function, so you're going to step towards the right, and this step is limited by the AU move limit. So you can see that if you take large steps, you'll obviously end up with a very big difference between your linear approximation and the actual function. So you have to limit the step size to maintain accuracy during the optimization. And this is obviously a local method. Unless you take big steps, you won't be able to escape from any local optimum. So one of the problems associated with this sequential linear approximation is that the step size is usually problem dependent too. And you have a conflict where the smaller steps you take, the more iterations you need to perform for the algorithm, but it becomes more accurate. And the larger steps you take, the quicker the algorithm will converge, but the more error you have. And another problem is if you have numerical noise. For example, if your function, the finite element analysis, will give you something like this. If you use a finite difference scheme for the gradient calculation, you can obviously have some problems calculating the correct gradient if you have numerical noise present. So there it's also very it's not beneficial to use small step sizes because you're going to have numerical noise and you're going to have to jump around. So larger step sizes will be more optimal for that type of problem. And this you won't find out until you actually perform the optimization, and you'll have to go look at the output to see if this is a problem.
So your finite difference in discretization of the function f
Mm-hmm.
is actually much smaller than your limits AU and AL.
Yes.
Because otherwise you can't calculate that gradient.
It'll give you problems.
Why should it be much smaller?
Well, the step size you take is to improve the objective function, right?
Yes.
So if you take step size on the size of the finite difference scheme, you're not going to get anywhere. So
So if you have a central difference, finite difference in code to calculate the gradient, you have to have at least the 2 points surrounding x0,
yeah, for a linear approximation.
right? And they're right next to x0
Mm-hmm.
to get that linear approximation.
Yeah. So after the approximation is created, it becomes a linear programming problem, and you optimize that. And then you take a step, usually constrained by your upper and lower move limits. And after that step is done, you get the new point, and you go evaluate the fitness at that point, and then you create a new approximation, and you iterate through this to perform the sequential programming optimization.
What made you stop at XL? What made you pick XL?
XL is just the last point in the after you take the step, the next point is XL.
But you have move limits.
Mm-hmm.
So what made you select? Like there's many different. I have this linear
Oh.
approximation. I can select any
Yeah.
points in it.
So your linear programming problem contains constraints, the objective function, and your upper and lower move limits. So those three will define where your final point will be. I'll go through an example problem in a few slides, and I'll show you.
If it's a linear, then wouldn't it always be at one of the two?
Not necessarily. The constraints could limit that, and I'll also demonstrate that later.
And so when you iterate, and you'll probably show this in the example, but just so I make sure I ask this question.
Mm-hmm.
When you iterate, you have this new XL. Then do you go back on your F curve,
Yes.
and then you go from there. You don't. You know what I'm saying? Because you calculate this.
No,
linear
no, you would. Then you will diverge from the actual. Yeah. No, you step back up
step
to
back.
where your actual function is. So
Recalculate the derivative again.
yes, you recalculate everything. You start from there.
So the whole point of the linear approximation is to So
Mhm.
you go along that until you've reached the extent of that, or you've satisfied that condition.
Yes.
And then you go back up to your curve there. And so it's basically to get you along the original function without having to calculate all the gradients in between those two.
Yes. Yes. Like a line search, we have to calculate every fitness along the search direction.
So it just gets you to take bigger steps.
Yeah, with the minimum amount of computational effort.
Right.
That's the whole idea. Okay, so the whole algorithm is stopped when a rate of change stopping criteria is met. So when you see that you don't achieve any sort of improvement in fitness anymore, you stop the algorithm, and that's usually determined by a tolerance that you select beforehand. So if you have a stress, you'll stop it when it certain changes what you want your final tolerance to be. Or you can check the Kuhn-Tucker optimality conditions at your final X point. The minimum at where?
You have your move limits.
Yes.
So that it's linear approximation.
Yes.
The minimum will be found in your limits.
Not
So
necessarily.
you will never converge to one solution, but always move.
Not necessarily. It's able to find a local minimum. I mean, I'll demonstrate this through an example, and I'll show you that it'll indeed converge. You get certain cases where it'll jump between 2 points, and then you need to stop at 2. That's when your constraints are in a certain configuration. So just to go through the example, if we have an analytical problem, and you can see the objective function is linear, so there won't be a point in linearizing that. You can just use the objective function, but both the constraints are quadratic functions, so we're going to use approximation on the quadratic function just for illustration. Usually that won't matter on a real life case. You'll have something like a finite element constraint or something like that. So we pick a starting point at 1, 1, and we select move limits as a unit of the current point. Usually you can select it as a range, a fraction of a range of a design variable, or you can select it as a fraction of the current value of the design variable. And if you go look through the examples in the handbook that Dr. Haftka posted, you'll see that the 2 examples use both methods. So just the constraint functions are then approximated as a linear function and evaluated at those 2 points, and then the derivatives are also calculated, and these are then used to create a linear programming problem. So these are the 2 constraints linearized.
So you just evaluated the derivatives analytically there.
Yes, yes. So if you look at the linear programming problem, the starting point will have move limits on this boundary over here. So it can only move a unit in each direction. The objective function will decrease in this direction. You can see that the contours are lines, and the constraints, the linearized constraints, are these 2 lines over here. So if you didn't use the move limits, your optimum will lie over here. So you can see that it'll take a very large step. It'll actually take it past the original problem's solution, and it'll overstep it. So with the move limits, it'll only take a reduced length, and the solution for that iteration is x1, and it'll lie on the intersection of the move limits.
Okay, the move limits are 2 and 2.
No, 1 and 1. You start with 1.
Right, but you already
Yeah,
Okay.
yeah. So the optimum for that iteration is 2, 2.
So you actually hit your move limits instead of hitting your linearized constraint.
Yes, yeah,
And then the dotted lines are your actual constraints.
yes. Those are the original problem formulation constraints. So as you iterate through this method, you'll see that once you start getting close to the actual optimum, these two constraints will move closer to that, and they'll actually fall within your move limits after a while, and the optimum that you'll get will lie on your constraints after a while.
Which one will move inside the...
Both the linearized constraints.
Okay.
So
But the other two constraints aren't going to go anywhere. 'Cause
the original ones? No.
the original ones
No.
are gonna stay there.
The approximation will get closer to the actual original one as you approach the actual solution.
But in this case, it looks like you're always going to be violating. I mean, as you improve your approximations, it looks like they're always going to be coming like this, and you're never going to have your linearized constraints, actually inside of your actual constraints.
Not during this step, but like I said, if I can try to show it to you. So if you have an objective function like this, and say your constraint lies here, then if you start off over here with your x0, and the approximation of this will be very far away, like indicated over there. But as you approach your actual optimum, these will start moving closer in your approximation. So the approximation of the constraints will become better as you approach your actual optimum. Is that?
Okay. I think I got you.
So the linearized G1 and G2 will start to converge to the original, the
Mhm.
G1.
Yeah.
But don't you want to make sure that they are more conservative than your original G1 and G2? 'Cause, I mean, looking at this, they look less conservative than your original G1 and G2. Do you understand what I'm saying?
Yeah.
Will they, as you get a more accurate prediction, become more conservative as you, like for instance, I understand this drawing, but as you get closer to that actual constraint,
Mm-hmm.
will it then just become conservative and we're just on the opposite side of that second derivative being 0?
Yeah, if you so let's try and make an analogy. If you approximate the derivative at this point, you'll get something like that, right? If you step towards this, you have a large error. As you move this closer, this becomes smaller and smaller and smaller, and when you get in the region of this, it'll be approximately the same. That's the same with the constraints. So your actual error will get smaller. It's the same as for the fitness.
And you just hope that your linear constraints are more conservative than your actual constraints.
I don't know if you're going to end up on the wrong side.
You end up on the wrong side when you come back though.
Yeah, if you overstep, you're going to be on the wrong side. Yeah. I have to go look into that. Okay. So the first iteration yielded that 2-2 solution, and the final fitness was -6. If the move limits were not imposed, it'll overstep and it'll be -22. So if you ignore the move limits, you get large constraint violations, and the objective function will be very inaccurate. It's due to this, as I showed on the board. So some advantages to this method. Most linear programming the linear programming problem is what you solve when you do the optimization after your approximation. So most programs like MATLAB, the numerical recipes in C, Octave, almost any mathematically based program will have a linear programming package that you could use to solve that problem. So that's relatively easy. The algorithm itself is pretty simple to implement. All you do is you have to create the finite differencing scheme to create the approximations, and then you can from that just solve a linear programming problem. And you only require first order derivatives for linear programming. Later on, when I discuss the quadratic programming methods, we'll have to go to higher order derivatives. And this first order derivative can be easily obtained using a finite difference method. There are some software considerations though. If you use a package like what is a common finite element package, Abacus or whatever, you don't always have access to the inner workings of a program to be able to calculate the derivatives. So sometimes that becomes a consideration on what you're trying to do in the software. And if you have a high number of design variables, this method is also a little difficult to use because your finite differencing method scales with the number of variables. So some disadvantages to this method is, like I said at the start, if you have large move limits, you end up with inaccuracies in the objective function and the constraints, and it might also prevent convergence. It might flip back and forth. So usually the other alternative is too small, which will require a large number of iterations of the program, and it'll translate to a excessive computational effort. So you have to decide on a linearly reducing move limits or some sort of a polynomial to just create an optimum scaling of your move limits. And this is obviously reduced as you approach your optimum. This reduction rate, however, is problem dependent, and usually what people do is they monitor the fitness value during the iterations. So if the objective value is larger or equal to the previous step, the usual reduction is 10 to 50% during the iteration. And a typical starting value is 10 to 30% of a design variable range, or you can just use a fraction of the current design variable value. Are there any questions so far?
In MATLAB, which is a function for
SLP? They have a fmin_con is SQP, yes. I don't know if you can linearize it. I'm not sure. I haven't had any experience using MATLAB on this. Okay, some other problems that this algorithm has, if you pick a initial design which is infeasible, it might result in steps that stay in the infeasible region. So it's never able to escape from infeasible constraint violation. And usually what is done then is by use slack variables to relax constraints, just to give it the ability to escape that. And I'll treat this in an example in a few slides. And the other thing that Victor asked was if the method might stay between 2 points and never get out of that loop, and this is when the optimum does not lie at a vertex. So in this figure, the optimum, after this gets close to the optimum, this optimum will lie at the vertex of the two constraints. So if there's only one constraint, for example, you might get the situation that the SQP or SLP will just flip between two positions on the constraint itself. And this may also be solved by just reducing the move limit, so it'll take smaller steps each time, and that'll shrink down to 0, and that'll be at your final optimum solution.
Do you ever change your move limits, like
Yes.
as you go, so your move limits will decrease each step?
Yes. So, for example, if there is an improvement, you don't reduce. But as soon as you see that the next step will give you a bigger fitness value instead of a reduction, or it stays the same, you reduce it a little. So that, so in this graph, you'll start off with a point. If this is your solution and this is the first point, if you take a step and you see that this is a reduction, you don't reduce it, and then you take another similar size step. Let me change this. I think about there. It still improves. Sorry, it still improves, but the improvement is not very great. And then on the next one, you actually increase again. Then you obviously know that you stepped too far. So then you reduce your move limit to something like this, and you take another step, and you see that the improvement is still, there's still an improvement, and you do that until you shrink down to such small steps that your fitness value will not change for a very long time, and then obviously you stop the algorithm. So just for the case where you have an infeasible starting point and the algorithm is not able to escape from the constraint violation, then you'll use a slack variable, which basically is just this beta parameter. And what this does, it allows the constraint to be satisfied for a certain value of beta. And this reformulated optimization, you also reduce this beta parameter as the search progresses. Is that understandable? No? So, okay. When you're in an infeasible region, say this is infeasible. You start here. Okay, the algorithm won't be able to escape this. So you move this constraint. It won't be able to go downhill because it's the penalties. Well, the constraints will prevent it from stepping out of this. So what you do is you include a slack variable, and what that slack variable does, it simply moves the constraint towards the infeasible side of it, and this length that's moved is beta, okay? And that makes it a feasible point. And then it can go to do its usual thing, and it'll iterate out of this. But during this optimization, you want to reduce this beta parameter too, because when you include it, you actually don't solve the original problem anymore. You want to reduce the effect of beta. So what you do is you minimize the beta parameter as well. It's an extra variable, and you also minimize it.
Why would it go to the right if once you move the, I don't understand what the difference is. If you move your constraint over, why would it go to the right? It's improving by going to the left.
Hmm?
Or no,
You're minimizing. Yeah.
So, but why wouldn't it, okay, fine, if the constraint's on the right, why won't it go down?
Well, if you look at the let me try to find an example. There is an example. I don't think I have it here.
It's in the books.
It is in chapter 6. I think it's 6.3. 0.3, I think. Yeah, just look into it. But it has problems moving in a infeasible. When it's in a constraint violation situation, it has problems escaping it.
Well, like, if that's your starting point, why not just have it evaluate everything at the one starting point and say, okay, it's infeasible.
Mm-hmm.
Pick a different.
Yeah, you can do that. But
Doing it.
some problems are over-constrained, and it's hard to find feasible regions. You can restart it. That's actually a strategy that most people use. They just pick a bunch of random points, evaluate it, see if the constraints are satisfied. But for some problems, you have a hard time finding it. Okay. So this extra design variable, beta, is also reduced during the search, and you can see there's a scaling variable k, and this is simply done to ensure that the minimization of this slack constraint receives priority over the objective function. So when it steps out of its region, the whole idea is to reduce the slack variable as quick as possible as well.
How does it ensure priority?
Well, if you have you weigh the beta parameter more than you weigh the objective function.
So k is always greater than 1 then?
No, k is a fraction.
Then its weighting gets less because the objective function is just get
Yeah, but the beta receives less weight in the objective function than it receives in the constraint function. So I'll address the beta in the constraint function first before it starts changing the objective function.
You said we want to prioritize to reduce beta
Yes,
over the objective function.
yes,
The objective function is just the first part.
yeah, but beta is contained in both, in the constraint and the objective function. So say you have a fitness of 1 and a beta of 100, and in the constraint will be violated, but because you add 100 to it, it'll be satisfied, right? And in the objective function, you'll have a very small addition. So when you minimize the objective function, the effect of beta is less because it's multiplied by a fraction than in the constraint function where it's not multiplied by a fraction.
Why even include it in your
Beta?
function? Yeah, why include beta? I think I understand why it's in your constraint, but I'm not sure why it's in your objective function.
Yeah, you need to minimize. You minimize your objective function. You don't. Your optimization is on your objective function subject to your constraints. So you don't actually worry about the constraints.
You wouldn't ever change beta if you didn't include it in your
Yeah.
That's right, but then beta
Yeah,
is
you're
a
right.
fraction.
It's not a fraction. It's
It
yeah.
should be greater than 1.
Yeah. Okay. Okay, just to demonstrate this in an example, this is a 4-beam problem. The areas are given on the figure, and it's subject to some compression and tension yield constraints, and the tip, deflection, and the y direction is also constrained. And if you calculate the forces in each of the elements, you'll get this bottom line, and the tip deflection, you can also create a function. So to make it a little easier, they non-dimensionize the design variables in the book and reformulate the problem into this form. And they also give some lower bounds on x1 and x2. And then they perform the SLP, the linearization for the first iteration, and they start off at point 1, point 1. First they evaluate that point, they get the fitness, and then after a approximating the. Okay, so on this problem is the reverse of the first one. The constraints are linear, so there's no need to linearize the constraints, but the objective is not a linear function, so they approximate the objective function in this case. So calculate the derivatives of the objective function, and then they take a step on the linearized problem, and they get a new point given on the bottom here, and FL is the approximated fitness, so that gives you substantial improvement over 47, so the step is taken. So the second iteration, the improvement is actually there's no improvement. Actually, the approximated function is higher than the old value. So what they do then is they reduce the move limits on the third step. So that's because the second answer was actually worse than the first answer, and then they perform 2 more cycles, and after stepping through them, you can see that the objective function does not change, so they decide to terminate the optimization. So basically what they try to demonstrate in this is you monitor your fitness value. If there is no improvement or if it worsens, you reduce your move limits, you take smaller steps, and then after cycling through that process, if it doesn't change any, you stop the optimization. That's the whole point behind this example. And as you can see in this one, the one constraint will give you the minimum. So if you look at the fitness, what do you call it? The fitness value, it'll rely on this one constraint, and it won't be influenced by these 2 move limits. So if you have a block where your move limits will start getting close to your actual optimum, you will stop against one of the constraints in the SLP problem. So
Your solution there is with 44.78 and your
yeah,
values of x that are at that point where it's tangent.
yes. So, okay, so the bonus problems for this lecture is first, I just want you to create a flow diagram of this method. And all I want is the flow of information, the calculations you need to do to get the approximation, and then also I want you to give me the reduction of the move limits using the rules in this section 6.3. So start off with a 10 to 30% and then reduce it 10 to 50% when there's no improvement. And that decision needs to be also in this flow diagram. And then example 6.3 is they use the Lagrange multipliers to in this approximation. So that's an extra part in the SLP that you can also use, and I just want you to solve that problem they do 1 iteration, so I just want you to extend that to 5 iterations. And then exercise 9 and 6.8, that's also just the SLP problem. Now, any questions on this?
For the first bonus problem, do we assume both the objective function and the constraints are nonlinear? Or should we?
Yeah, both are nonlinear, just to make it a general case. Okay. The reading assignment for next week. Just go through section 6.4. It's not very long. I have a paper that I'm going to post this afternoon that I want you to also to read through, which is actually a more descriptive literature on it, on the SQP. Any questions? Okay, thanks.